Why, hello, how's it going? It's nice and early. It's the favorite time for me to give a talk when people are still asleep. So, Cryptoeconomics, an introduction. This is the course that I'm working on, cryptoeconomics.study. I'm going to talk about it a tiny bit, but we're going to talk about a whole bunch of topics today because why not? It's a developer conference and I don't get enough of those. But last week, I did go to a cool, super cool conference called economics and computation. So this was a mechanism design, algorithmic game theory conference, and it was really interesting to see, all of these design patterns that people were working on, and they were, auctions and market design and congestion control, and there were tons of really interesting topics which I, as a crypto person, have become super interested in because of how applicable it is to our space. Now, if you do want to take a look at this, just to let you know, there are, Algorithmic Game Theory is a great book. Also, there's some lectures online which you can take a look at. Definitely worth the checkout. So, cool, that was awesome. But now, the thing that I noticed is, as I was talking to all these people, I represent people as Gerbils, as people may know. They have these, these cool mechanisms and these proofs why they're fair and, why they make so much sense. However, they're always wanting, oh, I really want this to be implemented. And this was a more academic conference. I'm sure that there are, algorithmic game theory conferences that do have really implementer focused. But it was really interesting to see, it was like this green field of cool economic mechanisms that are just waiting to be implemented. And so, meanwhile, I spend a lot of my time at crypto conferences where they have a lot of rainbows and other things. And then, in those, we have a lot of people, which is really cool. And also, everyone is building something. Everyone is ready to, create and ship something. And really, there's this dire need for, good economic mechanisms and good, systems to build. And so, the flame on his head is there's a fire burning inside that he needs to ship. So anyway. One thing that Vitalik has always taught me is that there's this cool these two communities. Vitalik is always saying, oh, the law of diminishing marginal returns, right? You don't want to be extreme on any end. You kind of want to have a little bit of both. So I'm sure that there's somewhere in the middle between a kind of application shipping focus and a academic game theoretical kind of analysis focus that we can have. And so it's really, I imagine that there's this really nice space. And I think actually this is where blockchain, when you start building dApps, this is where you kind of naturally go, right? You go from, you have to learn how to reason about incentives and do this adversarial thinking and, figure out how your mechanism is going to react. And at the same time, we have a lot of skills from the kind of web development and, peer-to-peer networking and shipping software, and we really need user-facing applications. This is not just kind of make-believe. These are economic mechanisms that will be deployed and used all the time. And so, we can use cryptoeconomics, I feel, right in the middle and, sprinkle in some Ethereum and, boom, 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 boom. And, we get the Web3 future with open source and privacy preserving, internet platforms and fair and decentralized and make sure that there's no central authority that's going to abuse its power. And, with this, guarantee, we have less risk and we know that our applications can be built on top of this, open source and free and not corruptible, censorable platform. And, that inspires this kind of ecosystem of applications and boom, boom, boom. And that's a bit of a bird's eye view. This is a black swan plus a owl face. And let's go into a little more detail, little more, laser focus. And so the things that I'm working on with regard to kind of cryptoeconomics, which is this pretty big term for building on these systems, is Casper, Plasma, Casper, and sharding. And so first I'm going to talk about Plasma because I like to pack way more information in these talks than humanly possible, especially in the morning, because it's like more fun that way. So one of the biggest problems that we have on these systems is we have, transactions which take forever and ever to load, right? We have wait 30 seconds, wait a minute for your transaction to go through. That's some crazy talk. So what can we do? Well, we can use Plasma, some nice, a very simple augmentation of the Plasma spec to get basically instant confirmations really, really easily. And it is kind of like a little state channel. But anyway, so what do? Well, we have our normal Plasma setup with a Plasma chain and a mainnet contract that has a bond mechanism, a single Plasma operator, proof of authority. And here's the kind of augmentation. We add a bond. So we say, okay, the Plasma operator is going to say, okay, I have here's $1 million. I'm going to lock it up in this Plasma contract. And now I'm going to go about my business, and we'll see how that bond is kind of used to make sure incentives are aligned properly. So first, we're going to create a Plasma block, and that Plasma block is not yet included on the main chain. It's kind of just floating out in the ether. And so now we're going to send it to the Ethereum. And the Plasma block will be included in the main chain, and now it is confirmed. So the way that it works is, right, we're creating this off-chain thing, and then we're committing to it on-chain. Now we have Sam. Sam deposits 5 ETH and receives that ETH immediately once the block is mined, but that ETH is now PETH, and it is spendable on this Plasma chain. So immediately create a new Plasma block. So now Sam is going to start watching both of the chains, not just the Ethereum main chain, which he had her ETH on originally. Now there's also Alice, and Sam wants to send a whole bunch of transactions to Alice, right? 2,500. Because we're doing this off-chain stuff, we don't actually, we're not as constrained by the, quote-unquote scaling limits of Ethereum. And if you want to know how to do these kinds of scalable systems, you can learn Merkle trees. Please learn Merkle trees. Merkle trees are amazing. I was going to include it in this presentation, but I remembered how much time I have. So the cool thing that we're doing now is we have the Plasma operator send a message back saying, I promise to include those transactions in the next block, right? And I promise to include only those transactions and no conflicting transactions. So what does that actually mean? Well, that gives the Sam and Alice this kind of instant affirmation that their transactions are going to go through. So Alice can go about her business and try to spend or send Sam whatever the product or service that Alice was providing. So the reason why we can do this is because either those transactions are going to go through or they're going to be burned. The operator's bond will be burned. And so let's look how that might work. So in the happy case, first we have the Plasma operator. The Plasma operator creates a block with all of those transactions, and the block hasn't been finalized yet. So the Plasma operator is going to send the block header to the main chain. The main chain will mine it, confirm the block, and we're pretty good. PETH has been transferred, reliably. So that's our happy case. Now, on the other hand, unfortunately, the Plasma operator could be malicious. We can't protect against that necessarily, but we can make it so that it is not in their economic interest to do so. So the Plasma operator is going to create a block which has conflicting transactions. You can see it's an evil block because of the horns. Now, this block will be submitted to the root chain and get confirmed just like before. However, this time we are going to say, okay, I noticed that the transactions were not included, and I also have evidence. I received that message saying, I promise that it will be included. And so Sam and Alice can just submit that evidence to the root chain, and the root chain will then act as a kind of mediator and burn the deposit of the operator. And so what does this actually do? This says, what the fundamental construct that you're working with here is you're saying, I have this ability to sign messages and assert things, and if I assert something that is deemed false by some mediation process, then I can be penalized or I can be rewarded, whatever your system is. And the reason why we can burn everything, well, number one, we have to, of course, hit that central operator. Gosh. awful guy. But now the reason why this is so easy to do is because it's a fully attributable fault. What that means is that we know exactly who was wrong in this circumstance. If you say one thing and then you do another, and we're able to prove that it was only you who made the mistake, then that is that's something that we can really penalize. And that's something that we use a lot in Casper. And also, unfortunately, not every fault is like this. Sometimes we can't distinguish between someone who is, doing something maliciously or someone who's doing something that, maybe is against the protocol, but it's not so good. Or maybe they're being griefed by another person. But that's, more content for another talk, unfortunately. But all of these things on cryptoeconomics.study, definitely take a look. So we just used some, very simple mechanism to kind of reduce transaction times. And so that's super useful. And I one of the reason why I wanted to bring this up is just because I really think that we cannot be waiting for transactions. It will be our user interface will be so much better if we have instant confirmations. So great. Now let's take a look at Casper success. So Casper has been this FFG hybrid Casper sharding research kind of huge project for many, many years. And this is going to be a kind of little update. And so we'll hear the way that you become a validator is you deposit ETH to a smart contract once again. And why deposits? Well, it's exactly the reason why we had the Plasma operator have a deposit, so that if anything goes wrong, we can kind of constrain their actions and slash them. So this is just a kind of quick review. I don't know how many people are familiar with the Casper protocol, but I've talked about it a lot, and so I imagine that hopefully some people have a reasonable idea. But I think even just by looking at this diagram, you'll be able to get some picture. So the Casper validators are going to be finalizing a proof of work chain, right? So this is the kind of hybrid Casper. We have the proof of work miners at the top. We have the Casper validators on the sides, and they're voting on checkpoints. And notice that when the checkpoint reaches 3/4, or actually greater than 2/3, then it is considered justified, which is yellow, or finalized, which means 2 justified checkpoints in a row. So there's actually a bunch of math that goes behind why 2 in a row makes sense. It has to do with preparing commits. Once again, I won't get into it for this particular talk. Now, we continue doing this. We continue finalizing and producing blocks with proof of work and justifying it and finalizing it with Casper. By the way, what finalization means is it means that either this block will be included in the main chain, or there will be a huge, if there are 2 conflicting blocks that get finalized, then a very large penalty will be, sacrificed for the evil validator. So essentially, what we're trying to do with any consensus protocol is we're trying to come up with a single history of transaction ordering. And so if there is ever a conflicting history, then something has gone horribly wrong. And so we've solved the kind of nothing at stake problem with these slashing conditions. And once again, these slashing conditions, you can definitely check out online. There's a bunch of talks which go over them. So in a POW attack, for instance, with a ASIC, or there's actually been a lot of crazy stuff with consensus protocols kind of misbehaving. For instance, the whole double spend on Bitcoin Gold, that's some crazy stuff. So the POW attack, this stuff is very real apparently. So if there's a POW miner which, for instance, has an ASIC and is able to create blocks really quickly, well, they still can't get a 51% attack. They still can't revert the history because they don't have the validators, signing off on their messages. So really, the thing that this says is that the proof of stake protocol is taking precedence over the proof of work protocol. So proof of work failed. Go Casper. Hallelujah. So now let's get into some fun new stuff, which is what I've been waiting for, and that is some nice Casper and sharding jazz mixed together. So what did we do? Well, the Casper thing that we've been talking about so far says, I'm going to send these messages, I vote for a checkpoint, and I sign the message. Now what we're going to do is we're saying, okay, let's take these messages, still the vote for a checkpoint, all of that stuff is the same, but let's add in a little bit more information. And that more information is going to allow us to construct shard chains more efficiently. And so or attestation, but I won't get into attestation so much. So how does this kind of like Randau beacon chain? So this is the kind of new thing. We're constructing a chain in parallel as we finalize another chain. It's some cool stuff. So Randau beacons. These are just like the 4 properties of hash functions, and what we're going to be using, each one of these is super important and you should know all of them, but random oracle is the key property that we want to exploit right now. And so what are we going to do? This random oracle property says that the output of a hash function is indistinguishable from a random number, and even the output of the hash of a hash function, hash of a pre-image, the hash of a pre-image is also a random number. And we can continue doing this over and over, and we call this onion hashing. So we're able to kind of generate a long string of random numbers by hashing repeatedly the same input. Now, this is the kind of core building block for the Randau beacon chain. Now, what does this mean? Well, the Randau state, we have a bunch of validators. Each one of them submitted a deposit. They have a public key. They have their Randau onion, and we're going to go over how that's generated. And they have 32 ETH. So this is a nice low deposit, relatively speaking. So generate onion. This is an important function. Essentially what it says is, okay, let's just generate a really huge hash onion. A hash onion that is just, one input seed, and that seed is kind of like a private key that is then used to, generate this entire long string of basically random numbers. And that is the reveal, and we're going to send the chain the last reveal in this hash onion. So what does that mean? Well, we're hashing and hashing and hashing. We create this long string of random numbers, and then we save the last reveal, so the very outermost peel of this onion. Now, what are we going to do? We're going to start with a single block. This block is just 0, default. And we're going to say, okay, who is the next person who is able to propose a block? This is where the randomness comes in, because what we're trying to do with this mechanism, actually, to say, is we're trying to say there is a large group of people. We want a random chain. We want a random selection of validators to produce blocks. And we want it so that there is no one person who is able to really manipulate badly the randomness unless you have a certain percentage of the network already. So what are we going to do for this? Well, we're going to start with 0, and we're just going to pick the 0th validator, and we're going to say, okay, reveal your last element in the Randau hash onion. And so in this case, we removed one layer of the onion, and we got the hash, A3C. Now, what we're going to do is we're going to submit that block, A3C, and we'll then, and we'll update the last reveal. So the way that this is computed, of course, is we just say A3C, we hash it, and we should get the output. And the reason why this works is because you can't actually reverse a hash function. That's another property of hash functions that was listed out. So once again, we're going to, mod 6, and we'll pick one of these validators, and this time it's going to be 4. And we will do the same thing. We're going to reveal the last layer of this hash onion, and we'll update the last reveal. And so we now have now we choose our next validator, which has the last reveal of 1AB, and we do the same process. And we pick another validator, and pick another validator, over and over again as we build up this chain. So what are we doing? We're actually constructing this very long string of randomness from a group of participants that are not necessarily coordinated. They can be coordinated, and hopefully they don't have a coalition of greater than 51%, for instance. But actually, something interesting is that in the mechanism that I just described, even if you had a 100%, a 100% coalition, you'd be able to predict the randomness, but you wouldn't actually be able to affect the randomness. However, this is because the Randau beacon that I just described does not have forking, and in the real version there is forking because of skips. But I won't get into that too much. I want to kind of give a reasonable intuition first. So why do we need this randomness? What is the whole point? Well, It is because we have this group of validators that are proposing blocks. These are, our block proposers, and we want to randomly sample block proposers. So every time we are, using this randomness to sample a whole bunch of these block proposers. Why do we want to do this? Well, it is because the entire problem that sharding is trying to solve is this problem where an attacker can pick the chain that they want to attack. What we will see is we'll see chains that have relatively small number of miners, and maybe they have a connection with an exchange like Bitcoin Gold, and they will attack that chain in particular to then exploit and steal a bunch of money. Now, what we want to do is, instead of having these kind of segmented groups of miners, we want to create a single pool, which then is randomly sampled. So you either get all or nothing. You're either going to attack the entire blockchain, which is running, a huge amount of applications and processing, and should have, billions of dollars in terms of deposits, instead of having the ability to attack small little chains that are vulnerable. So we're able to do this random sampling, and this is kind of the key. This is what sharding really is doing. So now, the beacon chain and the main chain, how do these interact? The main chain is kind of exactly the way we described it before with the proof-of-work hybrid Casper. However, now we are simultaneously building up the beacon chain with our Casper messages. So the Casper validators are going to be providing these RANDAO reveals over and over again, once again randomly sampled to create blocks. Now, the bottom checkpoint, right, we just justified. On the right, we are basically looking exactly the same as before. However, on the left, we are now creating this long string of random numbers, which is critical. And, oh, thank you, before it dies, good move. So, we are creating this long string of random numbers. Boop, 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 we're doing some more. And now, notice that actually, there's a couple, insights here. These actual pointers to the main chain, technically, there's a whole bunch of them, not just the ones that I showed. There's also each one of these blocks, we have, because we have a lower deposit size, we have a huge number of validators now, and so each one of these blocks is actually going to be not only the block, but also a huge number of attestations for that block, so that prevents forking. But to kind of get an idea, this definitely works. So we now have, we've justified what's it called? This one. We've justified this, and we have finalized the first one. So this is remember, once again, justified just means that you've reached 2/3 for that particular checkpoint, and then finalized means that we've reached 2/3 in a row, which means that if we ever get a conflicting history, then a huge number of validators will be penalized. And so we continue this way, and we build up our random beacon chain until our next checkpoint is justified, and these blocks are finalized. So we are doing two things at the same time. This is the really cool bit where we are simultaneously providing extra security to this proof of work chain. At the same time, we are building up this really solid source of randomness for our shard chains. So what does this actually look like from the shard chains perspective? Let's put the Ethereum main chain to the side for a second, and let's look at these shard chains. So the way that these shard chains are each one of these blocks on the beacon chain is essentially finalizing or checkpointing a block on each one of the shard chains. So not only do they serve as this kind of finality mechanism for the main chain, they're also serving this dual purpose of finalizing shard chain blocks. So it's this kind of a recursive finality gadget where we're using the same finality gadget on the top layer, and we're kind of iterating down to get lesser and lesser levels of economic security. So this is actually one of the key interesting points that you should, when you reason about these protocols, you think about it in terms of how much money would it cost for me to have my protocol essentially broken. So in our first case, we were saying, okay, it's $1 million if the Plasma operator were to misbehave. In this case, there's going to be different levels of security for the shard chain blocks that have just been created and the shard chain blocks that have been checkpointed in the Casper chain. And then there's going to be an even more security when you've been finalized in the main chain. So the maximum security is finality in the main chain. So, full proof of stake Casper without losing what we already have. So we basically have this nice augmentation where we're able to build up a solid foundation for the shard chains at the same time as we build up this Casper chain. So, with Casper sharding cryptoeconomics, we can do it. We can build a massively scalable future. So we've got our validators, and our validators are validating a whole bunch of shards, and each one of these shards has well-designed applications that take advantage of space-saving techniques like Merkle trees and using the blockchain efficiently. Because even when we shard, no matter how far you go, you're going to need to use good cryptoeconomic mechanisms that are not totally inefficient for like a Twitter, for instance. So I, at the same time as I'm doing all this research, I'm also working on a course where we go over core design patterns and concepts of cryptoeconomics and a coding project. And I would highly recommend checking it out. There's a forum, it's quite active. This is a completely open source project. There's a whole bunch of videos that I've already posted, and we're working on, there's chapters that have been produced by people that I don't actually know personally very well. Like, they just kind of came on the internet and wrote chapter 1, which is pretty amazing. This is a video lecture series and a book and a coding project. And so we've got a whole bunch of material that is coming out, trying to make it so that there's a pipeline for both mechanism designers and for these web developers that want to build cryptoeconomic mechanisms. So you can kind of get a taste. If you're a mechanism designer, you understand how the applications are built. If you're an application developer, you understand how to reason about incentives. So let's explore cryptoeconomics and build good things, and have a great time, and join the worlds, and make a lot of fun animations, because what is life if not a bunch of animations and Doge? So thank you very much. It's been a pleasure.